Okay, so what we looked at here was vertex form. And so it's y equals a times x minus h squared plus k. And when it's in that form, it's really easy to pick out the vertex. It's the opposite of what's with your x, which is your h. And what's added to the end is your y, which is k. Now, what I've done is I took and I expanded that binomial. I squared it. And what do we think when we're just squaring it? You square the first term. You double the product of the two terms. So x times h, and it's negative, so it would be negative hx. Doubled is negative 2hx. And square the last one. H squared is h squared. That doesn't look much like an h, but that's what it is. Okay, so now we have to distribute that a, right? So we get ax squared minus 2ahx plus a... Okay, that's a bunch of stuff, isn't it? But it looks like we've got an x here. So this is my square term, right? Did I miss something? Yes.
Why is it hx?
Because I distributed this a. And right here, when you double the product to get the middle term, you get 2hx. And that's where that came from. Okay, so here's my square term. Here's my linear term. And so what does it leave for these? This would be my constant, right? This would be all that. None of that has an x in it, does it?
Yeah.
So that's really just a constant. It's just a number. Okay. So let's compare this vertex form. This is vertex form up here with standard form. Standard form for a quadratic looks like this. Y equals ax squared. Come on, maybe. Here we go. Ax squared plus bx plus c. That's in standard form. Now, when we're in standard form, can you easily see the vertex? No. It's hidden somewhere in there. Now, c is not the vertex, but what would it be?
Oh, it would be the
Y-intercept. Because if we plugged in 0 for x, aren't we just left with c? So we can easily see the y-intercept. Woohoo! How does that help us graphing a quadratic? Not really. Yay! Okay, that does nothing for us. But can you see a quadratic term, a linear term, and a constant? Yeah. So if we compared these two, let's do some comparison real quick. All right, let's compare the quadratic terms. Ooh, they're identical, aren't they? Okay, so that's nice. Now let's compare the linear terms. Not so much. And the constants? Not so much. Okay. Now, when we looked at our vertex form, h represents the x at the vertex, doesn't it? What would happen if I took this, the linear term in one form? Shouldn't that be equivalent to the linear term in the other form? Yeah. Just like our quadratics were equivalent, that negative 2ahx should be equivalent to bx. Solve for h for me. Take that equation and solve for h. Let's see what you get. Does h simplify to negative b over 2a for you?
Yes.
Yeah. So if you're given standard form, to find the x coordinate at the vertex, all we have to do is say that x coordinate at the vertex, which we usually represent by h, isn't that equivalent to negative b over 2a? Alright, so why is all this helpful? What if I gave you an equation that was not in vertex form, but was in standard form instead? X squared minus 4x plus 6. Now, just staring at it, we can't really tell where the vertex is. So it's a little harder to graph. We just have to randomly pick x values and plug them in and hope for the best. Maybe we picked one that was the vertex. If we didn't pick one that was a vertex, we might have a graph that looks like just that. That's not very helpful. We really need that vertex. So we want to be able to find the vertex. Since this is in standard form, which is ax squared plus bx plus c, you can easily find the vertex by doing negative b over 2a. So the x value at the vertex, if you want to call it h, you sure can. It is negative b, which makes that a positive 4, over 2 times a. What is a in that equation? 1. So the x value at the vertex is 2, isn't it? 2. Let me switch this to f of x. Now, if I know the x is 2 at the vertex, how can I find the y? Plug it in. Find f of 2, which is 2 squared minus 4 times 2 plus 6. 4 minus 8 is negative 4 plus 6 is 2. So I know the vertex is the point 2, 2. Now, is it easy to graph? Yes. I know the vertex is the point 2, 2. A. This first one was the same in both forms, wasn't it? So the A here is the same as the A here, isn't it?
Yes.
So that tells me, is there a vertical stretch or compression? No, it's a positive 1. Is there a reflection? No. So from right here, I'll just do normal moves. Over 1 up 1, left 1 up 1. Over 2 up 4, left 2 up 4.
Alright.
Now, if I was lucky enough to pick the right numbers and plug them in, like if I plugged in 0, I get out 6. Is that on my graph? 0, 6. If I was lucky enough to pick 1, if I plug in 1, I get 1 minus 4 is negative 3 plus 6 is 3. Is there a point at 1, 3 on my graph? Yeah. If I got lucky enough and picked out 2, I get 4 minus 8 is negative 4 plus 6 is 2. Is that point 2, 2 on my graph? Yeah. If I got lucky enough and picked all the right points, then boom, I could have graphed it real quick without knowing how to find the vertex. But that's only if you get lucky enough. So having a nice shortcut that takes us right to the vertex makes life much better. So now that we know the vertex and we know there's no stretch or compression or reflection, could you write it in vertex form? What would it be? Y equals x minus 2 squared plus 2. Make sense? Okay, oops, there is your first example that I just did. Alright, here's your second example. Alright, this is obviously in standard form. We know the y-intercept is 5, but we don't know where the vertex is. So what do we do to find the vertex? The x value at the vertex is negative b over 2a. So that would be positive 4 over 2 times 2 this time. So what? Yes. X is 1. So if x is 1, I plug in 1 to find out what y is. So I get 2 times 1 minus 4 times 1 plus 5. So this is -2 plus 5 is 3. The vertex is the point 1, 3. So vertex form would be y equals, what is my A? Somebody said it. 2. Remember that first one was the same in both forms. So if there's a vertical stretch, if there's a 2 here in vertex form, there is also a 2. So it's going to be x minus 1 squared plus 3. Okay, what would happen if I squared this out, distributed the 2, and added the 3 to it? It would turn right into that, wouldn't it? And you can check me, but it does. It turns right into standard form. So if I graph this, my vertex is the point 1, 3. My moves are doubled, so over 1 up 2, over 1 up 2. That's all that fits on my little puny graph. Okay? Domain would be negative infinity to positive infinity. Range would be 3 to infinity. X-intercepts, none. Y-intercept, I can see it. 5. It is increasing from 1 to infinity. It is decreasing from negative infinity to 1. It is positive everywhere. The entire graph is above the x-axis, isn't it? In behavior, as x approaches positive and negative infinity, y approaches positive infinity. The axis of symmetry is x equals 1, and we have an extrema at the point 1, 1. The extrema is our vertex. And in this case, our extrema, I said, yes, 1, 3. I said 1, 1, but I meant 1, 3. And in this case, it's an absolute min. We have a minimum at the point 1, 3. Or you could say the function has a minimum value of 3.
Is that always, like, is the vertex always the extreme?
Yes, it is. For every quadratic, it certainly is. I was going to do a couple more problems. Don't even get out your notebook, but this is in our workbook. And it asks for the maximum number of albums sold. On which day was the most albums sold? We're looking for the extreme of this problem. And what Ryan just said was beautiful.
Vertex.
It's always at the vertex. So when it's in standard form, what's our shortcut? Negative b over 2a. Isn't that nice?
Okay, that makes sense.
Isn't that so nice? Doesn't it make it so much quicker for us?
That was the first time I got it.
Oh, okay, good. All right, you got it. You got it there. Okay, that's all we're going to do for today because I'm about to go over the test for this class.